What the rest of the unit is going to look like is there are 3 more large sets of identities we're going to cover in this class, something called the sum and difference identities, double angle identities, and half angle identities. I'm going to give you all 3 of those today. And then we are going to do practice with what I believe we will be able to get through sum and difference and then double angle identities, and we'll stop. I'm going to give you Friday off in order to work on the homework and the ALEKS. I will make myself available that entire day if anyone needs help. We will treat Friday as a work day. I will send out an announcement about this, but we will not be having class tomorrow, just to give you guys a work day and to slow down a little bit. Then Monday, we will go over the last tiny little bit of material that we have, which are the half angle identities. You will have those today. So if they ever appear on homework or you want to get ahead in the ALEKS, you will have them to work with, but we will be doing just a couple slides of practice with them on Monday. Monday will be a shorter class. And then what I think I'm going to do is Tuesday, I will be doing a kind of just practice day. And what I mean by that is my plan as of now is just to find some trig proofs and just do as many examples of trig proofs as I can on Tuesday, just because they're weird. Every single one looks different, and it can just help as a student to have more into your toolbox. So I think Tuesday, I'm just going to do a lot of examples of stuff. If anyone wants me to do anything in particular, like, hey, I'm struggling on trig proofs with Pythagorean identities, for example, please shoot me an email and I will work some in there. Or even, doesn't have to be proofs. It can be, hey, I'm struggling on solving this kind of equation. Because those are the main things we're doing in this unit, is solving equations and doing proofs. So if there's anything you want to review or go over particularly or do any kinds of examples of, that is what Tuesday is for, and I will be happy to do that. Wednesday, I will be doing the review for the next exam because our next exam is next Friday. I know it's coming up pretty quickly. So next Wednesday will be for that. I will put out the review early next week so you guys can get a head start. Along with your next week's homework that'll be due, I will put that out this weekend at the latest. And then Thursday, I have a math conference to go to. So I will be available by email, but not by Zoom. And then Friday will be the exam and I will be available all day. If anyone has any questions or stuff they want to go over or just questions on the exam in general. I've graded about half the exams, and if yours is graded, the grade is in WIO courses, so I would check on that. If not, I will get the other half of them done today. And I have most of your homeworks graded. I'm just going to put those in all at once when they're all done. So if those are not in, do not worry. Does anyone have any questions on anything? Okay. Then if there's no questions, we'll just jump right into what we are going to talk about today, starting with something called the sum and difference identities. So there we go. So in the past, we have learned the Pythagorean identities, we've learned the reciprocal identities, we have learned the cofunction identities, and a lot of those, I'm not going to say they were easy to understand, but we had a bit more of an intuitive sense for why they worked. Pythagorean identities, we're able to draw a triangle and show why sine squared plus cosine squared equals 1, and then we were able to derive the other ones from that. The reciprocal identities were just definitions we've been using. The cofunction identities we saw kind of visually when we did graphs of sine and cosine, cosecant and secant, and cotangent and tangent. And so we were all able to get a bit more of an intuitive sense for why those worked. These are a little bit more tricky, just at face value. I can't see right away looking at these why they work. And mathematically, they are like 10-line proofs. So it is not something really easy. It could just be like, oh, it works because of this. These are more difficult to prove. A lot of times people find it easiest just to remember these two. Again, you will always be able to reference your identity sheet, but what I'm trying to say is you don't need to worry about understanding why these work as much or trying to memorize them. Just know that if you ever have an angle plus an angle or an angle minus an angle, these are useful. And these identities are especially useful when we don't know at least one of the angles. So what do I mean by that? Well, this is an angle and this is an angle. Say we have something about like cosine of x plus pi. We would be able to split it up into cosine x cosine pi minus sine x sine pi. We know cosine of pi and sine of pi, so we could evaluate these two values right here to get them just into numbers. And then cosine of x and sine of x, we would be able to manipulate more to solve an equation. So these are useful when we don't know at least one of the angles. This here at the bottom, if you do want to try to memorize these, it is much easier just to memorize these forms of them. This is just an upside down plus or minus. So if we have cosine of alpha minus beta, it is cosine alpha cosine beta plus, and if it's the plus down here at the bottom, it's the minus. That's the only reason it's flipped upside down. But again, you don't need to worry too much about memorizing this one because understandably, it is not quite as intuitive as the rest of them, especially the ones for tangent. I've personally never bothered memorizing them. They are derivable just from the sine and cosine ones. But again, for your purposes, you don't really need to understand why these work or memorize them. Just know how they're useful in practice, which is what we're going to look at right now. So let's just do a little bit of utility practice to start, just to get a feel for how they work. I want to use a sum or difference formula to find the exact value of this. Okay, I could technically do this right now on my calculator, just plug in sine of 160 degrees plus or times cosine of 20 degrees plus cosine 160 sine 20. However, neither 160 degrees nor 20 degrees are special angles on my unit circle. So if I didn't have a calculator, I can't do this by hand, and I want to try to do it by hand. So to do that, I'm going to use a sum and difference formula. So this looks like the sine of an angle times the cosine of another angle plus the cosine of that first angle times the sine of another angle. Which of our identities on the last page does this look like? We had the sine of an angle times the cosine of an angle plus cosine of that first angle times sine of the second angle. To me, that looks like this guy right here. Sine alpha cosine beta plus cosine alpha sine beta. That is what this is down here. It's just that alpha equals 160 degrees and beta equals 20 degrees. So what identity is that? It is the sine of alpha plus beta. So all of this up here at the top is equal to the sine of 160 degrees plus 20 degrees, which is the sine of 180 degrees because I can add those two values together. We know the sine of 180 degrees. 180 degrees is just right here. The sine of it is the y coordinate on the unit circle at this point. And as we can tell, it is sitting on the x-axis, so this is just equal to 0. That was not very clear looking at that formula up at the top that this was going to be 0, but using the identity, we were able to find that. Any questions? That was just a little bit of a problem to get us comfortable with how to use these formulas. So let's try another kind of problem that's a little trickier. I want to use this information to find the tangent of alpha minus beta. And all I don't have alpha or beta. I have that the sine of alpha is 3/5, and I have that the cosine of beta is 4/5. That's all I have. I don't have anything about alpha or beta. So let me write down the formula for the tangent of alpha minus beta from this sheet up here, just so we know what pieces of information we need to look for. So to find the tangent of alpha minus beta, I do that by doing the tangent of alpha minus the tangent of beta all over 1 plus tangent of alpha tangent of beta. Okay, so the information I don't need alpha or beta, but I need the tangent of alpha and I need the tangent of beta. Cool, I can do that. Let's draw a picture of our angles to see if we can extract that information. Let's start with alpha. Sine of alpha is 3/5 with alpha terminating in quadrant 1. So let's say this is alpha right here. Sine is 3/5, and the sine of an angle if you remember our fancy little acronym SOHCAHTOA. Sine is opposite over hypotenuse. So that means this right here is 3 because it's opposite of alpha, and the hypotenuse is 5. What we need for the tangent is opposite over adjacent. So we need to solve for this adjacent side right here, which we can do via the Pythagorean theorem. We have 3 squared plus, I'll call this x squared equals 5 squared. 9 plus x squared equals 25. Hopefully a lot of you recognize this triangle right by now. This is kind of a fancy triangle because, as you can tell, x squared equals 16, which means that x equals plus or minus 4, because when we take square roots, we have to include both plus and minuses. The 3, 4, 5 triangle is nice. It pops up a lot. It's really nice when we recognize it. However, we know that this angle is terminating in quadrant 1, which means we're looking at a positive x value here. So x is going to be positive 4. So that's a 4 right there. Therefore, the tangent of alpha is equal to 3 over 4. We can also think of tangent, instead of thinking about it in the SOHCAHTOA sense, thinking about it in the y over r or y over x sense. Because if you remember from maybe like the second or third day of class, the sine of alpha would be equal to the y coordinate over the radius. Cosine would be equal to the x coordinate over the radius. And the tangent would be equal to the y coordinate over the x coordinate. It's the exact same idea as opposite over hypotenuse, adjacent over hypotenuse, and opposite over adjacent. It's just thinking about it more in the coordinate system sense. We're going to use these a lot. Okay. Now let's think about our other angle, which is beta. I'm going to take this guy and just move it out of the way. Let's draw us beta real quick, because drawing a picture always helps. Cosine of beta is 4/5 with beta in quadrant 4. So here's quadrant 4. Call that this angle here beta. Okay, so what do we have? We have a cosine is x over r, so it is 4 is the x coordinate over 5. We don't know the y coordinate. However, we can solve for it. 4 squared plus y squared equals 5 squared. 16 plus y squared equals 25. Y squared equals 9. It's that 3, 4, 5 triangle again. So y is plus or minus 3. We look at this, we see that, okay, because we're terminating in quadrant 4, our y value is negative. So y is equal to negative 3. The tangent is y over x. So tangent of beta is equal to negative 3 over 4. Cool. We have these two values. So now let's substitute them into our formula up here for tangent of alpha minus beta, and then we're done. So we still don't know alpha and beta, but that doesn't matter. The problem didn't ask for that. So we have tangent of alpha minus beta is equal to the tangent of alpha, which is 3/4, minus tangent of beta, which is negative 3/4, minus a negative 3/4, all over 1 plus 3/4 times negative 3/4. Just adding and multiplying these things out. 3/4 minus a negative 3/4 is just like 3/4 plus 3/4, which gets us 6/4, which is the same as 3/2. And then denominator, we have 1 plus negative 9 over 16. Cool. Adding that out in the denominator, we have 3/2 over 1 minus 9 over 16 happens to be 7 over 16. And then just dividing these fractions, we have 3/2, invert and multiply, 16 over 7. That's 48 over 14, which dividing out by a factor of 2 to simplify is 24/7. That is fully simplified. That is our final answer. Questions on how we did this one? A lot of times with these different kinds of problems, it's just about picking apart the information you have, seeing what you need, seeing, okay, this is my final destination. What information do I need to get there? Okay, what do I have? How can I use what I have to get to where I need to be? None of these problems are going to be exactly the same. They may need picked apart in different ways. The key skill to develop here is knowing how to approach them and how to pick your information apart. Questions here? All right, let's do another one then. Instead of just finding the tangent of an alpha plus beta, that was purely an evaluate problem, that was a solve problem. Now we want to find solutions to an equation, which is going to look a little different. So I want to find all solutions to this equation on the principal interval 0 to 2 pi. Cool. In the past, we've had to approach these with Pythagorean identities to get our trig functions to all be the same. Like if we had a tangent squared and a secant squared, we may have to approach with Pythagorean identity. However, we can't really do that this time because there's nothing squared about any of these. However, it does kind of look like some of our sum and difference identities. If you recall from what we did on the last slide, we have or not the last slide, the slide before, we have the identity that the sine of alpha plus beta is the sine of alpha cosine beta plus cosine alpha sine beta. Here we have the sine of x, which we can call alpha, cosine of something 3x, which we can call beta, plus cosine of alpha, which we called x, and sine of beta, which we called 3x. Cool, this form fits it. There's just one thing we have to do beforehand that doesn't quite fit the form that makes this a little bit different than our initial formula, and that's that we have to factor out a 2 because there's no multiples of anything in front of our sines and cosines, and there can't be, so before we do anything, we have to factor that 2 out. So that means that this up here becomes 2 all times the sine of x cosine 3x plus, we factored out the 2 from here as well, cosine x sine 3x is equal to -2, or negative square root of 2. Beautiful. Now that we have that, we can take this guy and turn it into the sine of alpha plus beta. We said that alpha was x and beta was 3x. So we now have 2 times the sine of x plus 3x is equal to negative square root of 2. I can add that x and that 3x together to get I have 2 sine of 4x is equal to the negative square root of 2. I want to get sine 4x by itself as much as I can, so I'm going to divide both sides by 2 and get that sine 4x equals negative root 2 over 2. Okay, we can't really do anything with the 4 inside though. So if you remember from last time, what we did in this situation was we said, I don't want to deal with that 4 in the argument here. It's nasty. I don't really know how to approach it. So for the time being, I'm going to just replace it with something else. I've already kind of used alphas in this problem, so instead I'm going to set 4x equal to u. I know I used alpha a lot in the last class. I just don't want to confuse our variables, but this will work the same if I just pretend 4x is u. So then I have sine of u is equal to negative root 2 over 2. So I want to find which angles u have a sine of negative root 2 over 2, i.e. when looking at the unit circle, what angles u have a y-coordinate of negative root 2 over 2. Well, drawing that picture, here's my unit circle. I would say y is negative root 2 over 2 about here and here. After drawing my picture, I can pretty easily see, remembering my unit circle, that these angles are 5 pi fourths and 7 pi fourths. Again, it's really tempting now just to stop here because, oh, we only want the solutions on the principal interval. We're done. We don't need to keep looking. We don't need to put these in the general form. However, because we are working with a substitution right here, we do need to keep going, and you will see why. This is the kind of problem we had to make the table for last time. So the general solutions for you our u equals 5 pi over 4 plus 2 pi k. K is an integer. We don't really need to specify that because this is just part of our scratch work. But also, u is equal to 7 pi over 4 plus 2 pi k. Cool. Now I want to substitute 4x in back for u because u is just 4x. We set that a while ago. So let's plug 4x back in for u so we can solve for x. We have that 4x is equal to 5 pi fourths plus 2 pi k, which dividing everything by 4, we get the x is equal to 5 pi over 16 plus 2 pi k. Similarly, 4x is equal to 7 pi fourths plus 2 pi k, which means that x is equal to 7 pi 16ths plus, this is not a 2 pi k up here, I messed up. You are supposed to divide everything by 4, so this is a pi over 2k, and this is also a pi over 2k. I just forgot, and this is a common mistake that a lot of people will make when you're doing these. You can't just divide this guy by 4 and this guy by 4. You have to divide everything by 4, including the 2 pi k, which feels uncomfortable because we're not used to not having a plus 2 pi k at the end, but it's why these problems work. Okay, any questions so far? Cool. Now that we have these equations here and here, we will use them to find all, because these equations, if you recall, describe all of the solutions to this equation. Let's use it to find all of the solutions within the principal interval. And to do that, we organize it nicely in a little table. The two equations we're going to be working with are 5 pi 16ths plus pi over 2k. I'm going to rewrite it as 8 pi over 16ths k, just so I have a nice common denominator. Similarly, we also are working with 7 pi over 16 plus 8 pi over 16. I don't know why I wrote an X there. K. Okay, so when k is 0, we have the solutions 5 pi 16ths and 7 pi 16ths. Cool. What about when k is 1? 5 pi over 16 plus 8 pi over 16 is 13 pi over 16. And then down here we have 15 pi over 16. Just 7 pi over 16 plus 8 pi over 16. Cool, we're definitely still in the principal interval. These, not only are they less than 2 pi, they're less than pi. So we're definitely good to go. When k is 2, add another 8 pi over 16, we get 21 pi over 16 and 23 pi over 16. Still in the principal interval, 2 pi is 32 pi over 16. So we're not there yet. Let's do another one. K equals 3. Add another 8 pi over 16 to both of these. We get 29 pi over 16 and 31 pi over 16. Wow, both still in the principal interval. All of these are still solutions in our principal interval. They are less than 2 pi and greater than 0. So we're still good. But you see, if we try for k equals 4, we get 37 pi over 16 and 39 pi over 16, neither of which are less than 2 pi. They're not in our principal interval. So in the interval 0 to 2 pi, we have these 8 solutions right here. And when you're doing these on your own homework, I would write them out nicer rather than just coloring them in with a highlighter like I'm doing. But just know that these are your 8 solutions. Questions on this problem? This one was pretty involved. We said, okay, we want to solve this equation. I don't know what to do with this, so I'm going to use a sum and difference identity to break it up like that. And then even once you used a sum identity, you realized, oh shoot, I still have a 4x in my argument here. That's not very nice. So you had to do a variable substitution with the 4x equals u. And then you had to find all of the possible equations for u, then solve the ones for 4x, and then make the table. These ones are pretty involved. Okay, let's do one that's a little tamer. We want to find the exact value of negative 75 degrees by using a sum or difference formula. Okay, so if you have your unit circle memorized, you'll recognize that negative 75 degrees is not a special value on our unit circle. We can't just use old values that we recognize to try to figure out what this is, because we don't know anything about 75 degrees. We don't know anything about its reference angle 15 degrees. We don't know what to do with this one. And notice I said exact value. You could plug this into your calculator any day and it would spit out a decimal, but anytime you see the words exact value, it wants something in terms of square roots and radicals and sums. It doesn't want 0.6192, etc. Exact means exact answer would be something like square root of 2. So in order to do that, we're going to need to manipulate this a little bit. Now, offhand, this doesn't really look like something we could use a sum or difference formula for. However, in a sneaky way, it is. If you'll notice, negative 75 is the sum of negative 30 and negative 45, both of which happened to be nice, beautiful angles on our unit circle. So what does this mean? It means that, well, instead of looking at the sine of negative 75 degrees, I'm going to look at the sine of negative 30 degrees plus negative 45 degrees. They're the same thing. All I did was just break 75 up into two numbers. That's completely legal. However, I'm now working with two angles, negative 30 and negative 45 degrees, which I'm very familiar with and can just look at my unit circle and tell you all of the trig values for. So let's do that. Again, I'm going to use the sum formula for sine because I have a sine and I'm going to use a plus. You could also just do negative 30 minus 45 degrees and use the difference formula for sine. It doesn't matter as long as you're consistent all the way through. But just using that formula we've been using for the last few slides, this gets us that we have the sine. It's, if you remember, sine alpha plus beta equals sine alpha cosine beta plus cosine alpha sine beta. So using that with our values of negative 30 degrees and negative 45 degrees, that's the sine of negative 30 degrees cosine negative 45 degrees plus the cosine of negative 30 degrees times the sine of negative 45 degrees. Just drawing these as a picture on my little unit circle because that's helpful sometimes. Negative 30 degrees is right here and negative 45 is about right here. On the unit circle, negative 30 degrees terminates at positive root 3 over 2, negative 1/2. And this guy right here, negative 45 degrees, terminates at positive root 2 over 2, negative root 2 over 2. So using that information and those values for sine and cosine, the sine of negative 30 degrees, i.e. where the y coordinate is negative 1/2 times the cosine of negative 45, which is positive root 2 over 2, plus the cosine of negative 30 degrees is positive square root of 3 over 2, times the sine of negative 45 degrees, which is negative root 2 over 2. Multiplying these all out, we get negative square root of 2 over 4 plus, or I'll say minus, because we're going to end up with a negative root 3 root 2, because positive root 3 times negative square root of 2 over 4. Subtracting these two equations, we get negative square root of 2 minus root 3 root 2 over 4, just combining the two fractions. I see a common square root of 2 I can factor out, so I'm going to do that just to simplify it as much as I can, which leaves me with negative square root of 2 times 1 plus the square root of 3, because I factored the negative out as well, all over 4. And this is really all I can do to simplify this one, and this is my answer. Notice this is ugly, but it is exact. It is what the problem asked for. There are no decimals. There are no oh, my answer is about 21.275. This is the exact answer in terms of square roots. So anytime you're doing your homeworks or exams, keep an eye out for terms like use a calculator or round versus find the exact. If you ever see the words find the exact value, I do not want a decimal. Leave it in terms of square roots. Questions on this one? All right, now that we're a little more comfortable, I think, with using these identities just to solve problems, let's try a couple proofs. So I want to prove the identity cosine of x minus y over cosine x cosine y equals 1 plus tangent x tangent y. So I want to decide which end I'm going to start and end on. Looking at the bottom part of the equation down here, I don't really know what to do with it. I don't really know what I could do. I could turn the tangents into sines and cosines, but beyond that, I don't really know what I would do. However, looking at the top one, I immediately see a cosine of x minus y. So my brain immediately is like, oh, I could attack this with a difference identity. So even though that may not work and that may not be what we need to do, I'm going to just try it and see if it works. So if we remember from a few slides ago, sorry, I keep flipping back, we have this difference identity for cosine of alpha minus beta, and it's cosine alpha, cosine beta plus sine alpha, sine beta. We can use that right here for cosine of x minus y. We can use that to rewrite it as cosine x cosine y plus sine x sine y, just directly applying our identity all over cosine x cosine y. And I did use an identity at this step, so I'm going to write off to the side by difference identity, or by the difference identity, I guess. Cool. Now what can I do? Well, I like in the numerator and the denominator that I can see that I have a common cosine x cosine y. So this is not something we usually do. We usually think about combining fractions, but I want to do is take this sum up here and split it into two fractions. Like, for example, how we know that we can do 4/5 plus 9/5 equals 4 plus 9 over 5. I'm going to take it from this step and break it down like this, because that's legal. If we can mathematically go forwards to combine two fractions, we can always mathematically go backwards, because math is really nice that way. So let's do that. Let's break it into two fractions. We just have the cosine x cosine y over cosine x cosine y plus sine x sine y over cosine x cosine y. Now, it may not be immediately evident to you at this point, but it is actually, we are pretty much done at this point. What happens here? Cosine x cosine y divided by cosine x cosine y, that is something divided by itself. That is equal to 1. Okay, then sine x sine y over cosine x cosine y. Sine x over cosine x is tangent of x. And then it's multiplied by something else. Sine y cosine y, that's the tangent of y. And what I use to get to this is by quotient identity. And notice I only wrote this line just to kind of talk out my thinking, but I didn't even need to do that because it's already written down here because it's our final destination. This one was not too bad. I agree that looking at it right away, I was like, I have no idea how I'm going to make this top guy look like the one on the bottom. They really don't look anything like each other. A lot of times the thing with these proofs is just trying to whack them with things. It's like, hey, I've seen something of the form like this before. Let me try to hit it with an identity. And then a lot of times, more times than not, what we're looking for will kind of just fall out nicely because they're designed that way. They're not designed to be completely impossible. Questions on this one? All right, let's try one more proof for now. I want to prove the identity sine of x plus pi over 2 over sine of pi minus x equals cotangent of x. Again, there's not much I could do with the cotangent on the bottom. I could turn it into cosine of x over sine of x using the quotient identity, because I know that's something I can always do. However, once I have cosine x over sine x, what the heck would I do with it? I don't know. So the only really reasonable way to work with this one is forwards. And again, looking at them, I noticed, hey, I have a sine sum identity and a sine difference identity. Cool. I can use those. Except on the bottom, I'm not going to use the difference identity. Hopefully we all agree that pi minus x is equal to pi plus a negative x. So just to simplify my life so I don't have to use multiple identities, I am just going to use the sum identity for both the numerator and the denominator, treating negative x as my second angle, treating negative x as my beta. And you'll see why that works really nicely. So doing that, just applying the sum identity to both the numerator and the denominator, which also seems like a good idea because we have a pi over 2 and a pi here, which is something we know we could evaluate. This fraction turns into sine of x cosine pi over 2 plus cosine of x sine of pi over 2 all over, I'm going to apply it to the bottom as well, sine x, or sine pi, my bad, cosine negative x plus cosine pi sine negative x. Okay. Before I do any more simplification, I'm just going to evaluate this. I know the cosine of pi over 2. I know the sine of pi over 2. I know the sine of pi. I know the cosine of pi. So I'm just going to evaluate those expressions in there before I move on. But before I do that, I'm going to make sure to indicate off to the side that this step was done by the sum identity. Always making sure label. Cool. Now I'm going to evaluate this to get sine of x times the cosine. Here's pi over 2. The cosine of pi over 2 is the x coordinate of the angle pi over 2 in the unit circle. That's 0. So we have sine of x times 0 plus cosine of x times sine of pi over 2, which is 1, all over the sine of pi. Pi is right here. The sine of pi is the y coordinate on the unit circle of that point. That happens to be 0. So we have 0 times cosine of negative x plus cosine of pi, which is the x coordinate. That is negative 1 times the sine of negative x. And just rewriting this a little nicer, because when we multiply stuff by 0, it goes away completely. Sine of x times 0 is 0. So in the numerator, I just have the cosine of x all over negative sine of negative x. Okay. Because I decided to use the sum identity instead of the difference identity, which you absolutely could have used, I just didn't want to have to think about two formulas for this one. I just used one, but you absolutely could have done it and it would have been just as correct. But because I did it this way, I have this pesky, oopsies, negative x in here. I don't really know what to do with that. However, if you remember, we did the even and odd identities last class, where we learned that the negative sine of theta is equal to the sine of negative theta. I have a sine of negative x. It seems I can just pull that negative sign out because it is an odd function. So doing that, I have the cosine of x over negative sine of x. And I need to indicate that this was by the even and odd identities. I just didn't like that negative sign in there, so I pulled it out. Notice that a negative times a negative is a positive, so this just leaves me with cosine of x over sine of x. Hey, cosine of x over sine of x is cotangent of x. And we did that final step just by using the quotient identities. So this one was a little more complicated, but still not too bad. We saw that we had some sums of angles in our first part, especially of angles we know, like pi over 2 and pi. So it's, hey, I don't really know where I'm going to go with this, but I'm just going to try hitting it with that identity to see what happens. Things canceled beautifully, and we were left with only this after only applying that sum identity. And then I said, hey, because of the way I did it, I have a pesky negative x. So I pulled it out, and then things just kind of fell nicely into a cotangent of x. Questions on this proof? All right, let's solve one more equation. And this one's actually not too bad. I want to find all solutions to the equation cosine of pi thirds plus x plus cosine of pi thirds minus x is equal to 1. Again, I don't really know how to deal with this in here yet, the cosine or the pi thirds plus x, but I know that I have the identity cosine alpha plus beta equals, that's not an equal sign, equals cosine alpha cosine beta minus sine alpha sine beta. And this is the same expression for when we're talking about cosine of alpha minus beta. This just turns into a plus over here. So that's why the upside down plus or minus happened. We can just use this identity right here to attack this part of the problem, and then maybe things will look nicer and simplify for us. Let's try. So let's rewrite this. We know that alpha is pi over thirds and beta is x. So using the formula, we have cosine of pi thirds cosine x minus sine pi thirds sine x. Now, attacking the second problem just with the difference formula for cosine, we have plus cosine pi thirds cosine x plus sine pi thirds sine x is equal to 1. Looking at this right away, I see I have a term that's a negative sine of pi thirds sine x and a positive sine of pi thirds sine x. So these two are actually going to cancel each other out, because when we add something to itself, or the negative version of itself, it's 0. So we only have to deal with the cosine pi thirds. We now just have 2 cosine pi thirds cosine x equals 1, adding like terms. What is the cosine of pi thirds? Well, this is the angle right here. We're looking at the x coordinate, that is 1/2 on the unit circle. So the cosine of pi thirds is 1/2. 2 times 1/2 cosine x equals 1, which really conveniently just simplifies down to the cosine of x is 1. That's beautiful. Who would have thought that this equation up here was just asking us when is the cosine of x 1, i.e. what angles x on the unit circle have an x coordinate of 1. Well, looking at the unit circle, we have an x coordinate of 1 right here, and that is the only place where the x coordinate is 1. That angle in the principal interval is just 0. So x equals 0. But because we want all solutions to the equation, we need multiples of 2 pi from 0, because we know 0 is 1, we know 2 pi is 1, 4 pi, 6 pi, 8 pi, etc. So x is just equal to 2 pi k, where k is an integer. Technically, if you wanted to write it out how we have been, it's 0 plus 2 pi k, but because we don't need to attach a 0 to it, because who cares about adding 0, we can just write 2 pi k, where k is an integer. Questions on this one? All right. Well, if there's no questions, let's start exploring the new identities a little bit, i.e. the double angle and half angle formulas. So they look a little scary at first, but this is what they are. And we use these when we have something like a double angle, like if we have 2 times some theta we could be able to approach, or theta over 2. Like say we know how to attack 5/4, but we want to know something about 5π8. We would use a half angle formula, or if we knew something about what's a good one? Double angle ones don't come up as much in evaluation. Half angle ones come up more in evaluation. These are both really useful for proofs. And notice from the sum identities that we just did, the sum of difference identities, sine of 2 theta is just the same as if we did the sine of theta plus theta. It's just a special case of the sum formula. You could plug it into the identity to see that for yourself. But this is just the special rewritten version of the sum formula, the sine formula for theta plus itself. Similarly, this is just the cosine of theta plus theta. Notice, however, we have one form for the sine equation. This is the one we typically use. However, there are 3 forms for the double angle formula for cosine. Why is this? Where do they come from? Well, the first one is just the most simple, easy to find version of cosine of theta plus theta using the cosine sum identity. However, remember from Pythagorean identities that we know that sine squared of theta is just 1 minus cosine squared of theta. That's just the Pythagorean identity. If we plug 1 minus cosine squared theta in for sine theta into the original equation, we get cosine squared theta minus 1 minus cosine squared theta, which is just 2 cosine squared theta minus 1. Hey, that's that one. Same thing would happen if we plugged in cosine squared theta equals 1 minus sine squared theta. We would get the bottom one right here. So that's where those come from. The one for tangent and all of the half angle identities are a little bit more difficult just to derive and intuitively understand. So we are not going to worry about them. Just know that you have them in your toolbox for if you ever see something like this, you might be able to approach. And if you don't know what that looks like right now, we're going to do a couple of examples of when these kinds of formulas would be useful. Any questions yet? Okay. So let's just start then by doing a really simple example of what these are going to look like, just so you can kind of get a feel for the formulas. We want to simplify the expression using a double angle formula. 1 minus 2 sine squared of π/5. Does this look like any of our formulas up here? Oh, hey, we have a 1 minus 2 sine squared theta equals cosine of 2 theta. I'm just going to write that here as a note. The cosine of 2 theta is 1 minus 2 sine squared theta. Notice that this is the exact form of this, where theta is π/5. So therefore, 1 minus 2 sine squared of theta equals cosine of 2 times π/5, which is cosine of 2 π/5. We don't know this angle. It's not a special one on our unit circle. So that's just our final answer. Again, this one was really simple. This was just to kind of get a feel for this is how we could use it, going in the direction of we have something like this and being able to look at our identity sheet and say, hey, I have an identity of this form on my sheet. Maybe I could plug this other thing in and see if it works. Questions? Okay, now let's look at an actual problem where we can use this in practice. I want to find the sine of 2x if the sine of x is -1/√10 and x terminates in quadrant 4. Again, I don't know what x is. I just know it's sine. So I could use, hypothetically, the double angle formula for sine of 2x to find it using just this information here. So first, let's look at what the formula for the sine of 2x is to see what information I'm looking for. Looking back at our identity sheet, I know that the sine of 2 theta is 2 sine theta cosine theta. So I'm just going to make a note of that. Sine of 2x equals 2 times sine x cosine x. Beautiful. So I just need sine x and cosine x. I already have sine x. That's half the battle. All I need to do is use the information I have from sine x to find cosine x, and then we're golden. Let's draw a picture. I know it terminates in quadrant 4. Boop. And I know that sine is y over r. So I know that my r here is square root of 10 and that my y value here is -1. So I need to solve for this side here. I need to solve for x. To do that, I can use the Pythagorean theorem because I'm working with a right triangle. X squared plus -1 squared is equal to the square root of 10 squared. X squared plus 1 is equal to 10. X squared equals 9. Therefore, x equals plus or minus 3. I know that my angle terminates in quadrant 4. So this x value here is positive. We are on the positive side of the x-axis. So x equals positive 3. Remember, the cosine of x is equal to the x-coordinate over the radius. So we have 3 over square root of 10 is the cosine of x. Cool. Now all I need to do, I have sine x, I have cosine x. That's all I need to find the sine of 2x apparently. So I'm just going to plug them into our formula. Sine of 2x is equal to 2 times the sine of x, which is -1 over square root of 10, times the cosine of x, which is positive 3 over square root of 10. Multiplying those two fractions out, I get 2 times -3/10, which is just -6/10, simplifying to -3/5. Questions on this one? Again, I didn't need to know anything. I didn't need to know X. I didn't need to know anything fancy. I just drew a picture with the information I had, was able to get cosine of X because I knew from the formula I was going to use to solve. I only needed the sine of X and the cosine of X, didn't need to find any extra information. Okay, let's do one proof and then maybe one more example, and then we will be done for today. I want to use double angle properties and maybe some others to prove this identity here. Okay, I have 1 over tangent of x times 1 plus 2 cosine of x equals cosecant of 2x. All right, now what should I do to approach this one? Honestly, I'd be comfortable starting either from the top or the bottom here. I think if I started at the bottom, I would just be setting things up a little bit for us. I don't think I'd be able to actually finish the problem if I start at the bottom, but I think I can get a little bit of information to maybe get a clear idea of where I'm going for the top one, because these don't look like cosecants at all. So maybe if I can turn cosecants into other trig expressions, maybe I can get a clearer idea of where I need to go with the top one. Again, you could start at the top one if that's where you felt comfortable. You could start at the bottom. There is no wrong way to do these. But just for this one to show a little bit different way of doing it, just than going straight through it, I'm going to start at the bottom just for sake of example. Looking at this, I don't know anything about the cosecant of 2x, but I do know from the reciprocal functions that cosecant is the reciprocal function of sine. So I know right away I can rewrite this as 1 over sine of 2x. This was by reciprocal identities. Again, we have to label them as if we're reading them forwards. I got 1 over sine 2x into cosecant 2x by the reciprocal identity. Cool. Now I have sine of 2x, and I do know something about that. Even just looking at the last slide, I know that the sine of 2x is 2 times sine x times cosine x. So I could even rewrite it like that. I could rewrite this as 1 over 2 times sine of x cosine of x. Cool. And how did I get from this step to this step? I got there by a double angle identity. Okay, now I've worked backwards pretty much as far as I think I can with this one. I am more comfortable with how this looks versus how just the cosecant of 2x works, because I have some cosines in here already and I have a tangent. So I think I may know now a little bit more comfortably how to manipulate the first one and how to see where I'm going. But I don't really know what else to do with this one. Maybe some of you do, but I'm not really comfortable going forward with this one anymore. I think I want to try to manipulate the top one a little bit. Okay, I know I want sines and cosines. I know I'm eventually going to want sines and cosines in the denominator. I have a cosine already, but I have this nasty tangent and I just kind of don't want to deal with it. So what I'm going to do right off the bat is just get rid of the tangent and turn it into sines and cosines, because that's always a good strategy to do when you're trying to get things in terms of sines and cosines. So all I'm going to do for the first step, I know I see this double angle here. I'm going to mess with that in a minute. Just in a second, I'm just going to deal with the tangent first, because I don't really know what identity I'm going to use for cosine yet, and I'll explain that in a minute. So just getting rid of the tangent, I have 1 over sine x over cosine x. That's just tangent by the reciprocal identity, or the quotient identity, times 1 plus 2, or cosine of 2x. Cool. I'm going to make sure to label. I used an identity here. This was by the quotient identity. Cool. Now that I have that, I need to think about cosine 2x. Unlike the sine of 2x on the bottom, there's not just one way I could substitute that in. The sine of 2x I know has to be 2 times sine x times cosine x. But for double angle identities for cosine, I know I have 3 to choose from. I have this one, and this one. I have something involving cosine squareds and sine squareds. I have something involving just cosine squareds and something involving just sine squareds. Let me look at my final destination of where I want to be. I have a singular sine x and a singular cosine x in the denominator. So conveniently, I already have the sine x here. That sine x is staying. That is the sine x I want. It is good to go. I want it there. However, I have this nasty cosine x in the denominator here that I want to get rid of. I don't want to add in any more sines because I already have the sine x that I need. However, I think I want a cosine squared in there so I can get rid of this nasty little cosine right here that's getting in the way of my sine. Is there an expression of the double angle identities that looks like this that only has cosine squareds? Yes, it is the middle one. It is 2 cosine squared theta minus 1. Again, this one may not work. And if you didn't really think through that process of which one should I use, you can always just try all 3. There is no harm in trial and error. It helps you realize why these things work sometimes. But for now, I'm going to use the middle one because I think I don't want to add any more sines into the equation. I already have the sign I want. So I'm just going to try that middle one, 2 cosine squared theta minus 1. So I'm just going to do that. I have 1 over sine x over cosine x times 1 plus 2 cosine squared x minus 1. Cool. And how did I do that? I used a double angle identity. Beautiful. Notice that this one and this one cancel each other out when we evaluate them. So we're just left with 1 over, and I'm going to multiply this sine x out. So I have 1 over 2 times cosine squared x sine x over cosine x. And all I did there was just cancellation in math. That was just a multiplication. So I don't need to label anything there. Now, it may not be extremely evident at this point, but notice that we're actually done. We have an extra cosine up here that we cancel with the cosine in the denominator, and we're just left with 2 cosine x sine x in that denominator, which, hey, is exactly what we have right there. So the step to go from here to here was just algebraic cancellation as well. So this proof is actually done. You can notice we started, okay, we took this guy here, turned the tangent into sine over cosine by the quotient identity. Then the next step, we said, hey, I don't like this cosine 2x. I'm going to use a double angle identity to get rid of the 2x in the argument. Once I did that, I said, hey, I can just algebraically cancel some stuff, algebraically cancel some more stuff. Hey, I have 2 sine x cosine x by the double angle identity. That is just sine of 2x. And then by the reciprocal identity, we just get to cosecant of 2x. Questions on this one? Again, these will feel much more comfortable the more you do on your own. I know they're weird, especially because it's not just doing the same thing over and over, but they will make more sense the more you do on your own. And if any of you want more practice, Alex has some great practice and I'm always happy to send you more of them. And that is why my plan next week is just to go through on Tuesday as many of them as I can in one class, just so we can get some more practice with what they look like. Okay, let's do one more and then I'm going to call it for today. And this isn't even a proof, this is just solving an equation. I want to find all solutions to the equation cosine of 2x plus root 2 cosine of x is equal to -1. I can see right away, I probably don't want this 2x in here. I can't, and in the past when we saw something like this, we'd say, oh, let's set alpha equal to 2x. We can't do that here because there's a 2x here, but there's not a 2x here. So we wouldn't just get to replace everything with alpha. This would end up being alpha and over 2 here, which is even messier. So I want to use a double angle identity to get rid of that cosine 2x. And I don't want to use one that involves sine squareds because then I have a sine squared and a cosine. So I'm going to use the double angle formula that only involves cosine squareds because that is much nicer to deal with. If you remember, that identity, we just used it on the last slide in our proof, is cosine 2 theta equals 2 cosine squared theta minus 1. You plugging that in right here, that gets us 2 cosine squared theta minus 1 plus square root of 2 cosine x is equal to -1. Adding 1 to both sides, I get 2 cosine squared x. That should have been an x, not a theta. Plus square root of 2 cosine x equals 0. Okay, beautiful. We have a common cosine of x in each of these that we can factor out because we're just solving our equation now. So we're left with the cosine of x times 2 cosine x plus square root of 2 is equal to 0. Cool, I have my equation in factored form now. I need to set this factor equal to 0 and set this factor equal to 0, solve them individually. Setting the first factor equal to 0, I want to know where the cosine of x is equal to 0, i.e. I want to identify angles x whose x coordinate on the unit circle is 0. Drawing our little unit circle here because it's always helpful no matter how many of these you do. The x coordinate is 0 here and here. That is at the angle pi over 2 and 3 pi over 2. Now, because we want all solutions, we need to write this with the 2 pi k's at the end. However, notice for this one, we're at pi over 2 here. We walk around the circle pi till we're at 3 pi over 2. Then we walk around again pi and we're at 5 pi over 2, pi, 7 pi over 2, pi, 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 just around the circle, excuse you, in steps of pi. So we don't need 2 separate equations for 2 separate solutions. Because we're only taking steps of pi, we can write this as one equation, i.e. we can say that x is equal to pi over 2 plus pi k, because we're just walking around in steps of pi, it hits all the solutions. K is an integer. Cool, that's one of our solutions. Let's see if any more solutions fall out of the other factor. So we want to find when 2 cosine of x plus the square root of 2 is equal to 0. Adding or subtracting a root 2 from both sides, we get 2 cosine of x is equal to negative square root of 2. So therefore, the cosine of x is equal to negative root 2 over 2. Now I want to think about which values on my unit circle have an x coordinate of negative root 2 over 2. That happens about here and here. This angle and that angle. This angle right here is 3 pi fourths, and this angle down here is 5 pi fourths. So our 2 solutions in our principal interval are x equals 3 pi fourths and x equals 5 pi fourths. There's no nice way to walk around in multiples from these 2 solutions because it takes 2 pi over 4 to get here and then 6 pi over 4 to go back around. So we are going to have to write these as 2 separate equations, but we can do that, that's fine. So the general solutions for those is x equals 3 pi fourths plus all other angles coterminal to it, so 2 pi k. K is an integer. Also, x equals 5 pi fourths plus 2 pi k, where k is an integer. And those are all of our solutions. We have all of the angles coterminal to pi halves, 3 pi halves, 3 pi fourths, and 5 pi fourths. Questions on how I did this one? Okay. What we're going to do next time, this is actually the end of practice for double angle identity, so I'm going to stop here. All we have left in this unit, shockingly enough, I know it is day 3 of lecture of stuff from this unit, but all we have left is that little bit of practice with half angle identities. This unit is very short in content, and that is because the content is more difficult. The proofs are not very formulaic. You have to think about how to approach them in different ways. So this unit is more of a skill building unit rather than just a knowledge building unit, which is why there's not a lot to cover. So next week is going to be very much a work style week, as well as this Friday is going to be a work day. You have some simpler proofs on the homework for this week. I didn't give any that were too tough. You should have been able to do all of them as of yesterday, maybe even as of Tuesday. I will make myself available tomorrow to help with those. Next week, we will do the half angle identity slides on Monday. Class will probably be about half an hour, if that. There's not that much to cover there. And then Tuesday will be the day where I just do as many examples as I can. Please, if there's any kind of example you all want to see, email me. I will be happy to throw one in there. I haven't written what I'm going to do yet, so let me know if there's anything you want to see done, or a couple examples of anything, or even a specific example from Alex. Speaking of Alex, your Alex module for algebra review is due tonight, and then the modules about trig proofs start to open up. Those can be a little tricky, so if you have any questions, email me or come to office hours, or just ask me if we can do a Zoom meeting. I would always be happy to. But yeah, that